Today we are going to design a rigid flange coupling. Okay, the inputs given are the shaft power. What is the power the shaft has to transmit is 120 kilowatt at a speed of 1500 rpm. Then the material, it's a hot rolled 1020 steel. This material has the following properties, like ultimate tensile strength of 450 Newton mm squared or megapascal, and the yield strength of 300 Newton mm squared or megapascal. Okay, fabric strength 330 Newton mm squared. The elongation is equal to 36% in 50 mm, and we have to make sure that the two side shafts are connected using this rigid flange coupling. The factor of safety n is equal to 2. So let's start doing the design calculation. The P is power. It is kilowatt. It's in kilowatt unit, and this one is in RPM. Okay, revolutions per minute. Now using the torque power relation, 9550 times P divided by N is equal to 764. It's a calculated value. Okay, this one is now 764 Newton meter is the torque. Okay, at the shaft. Now for that torque, using torsional shear stress formula, we are going to determine the shaft diameter. Using the formula, tau allow is equal to tau allow is equal to 16 times T divided by pi d cube. Allowable shear stress with the factor of safety is nothing but our yield strength divided by 2. Okay, yield strength divided by factor of safety n is equal to 2 is the allowable shear stress. Okay, the allowable shear stress is 150 Newton mm square. Okay, now we have the T torque and allowable shear stress, and solve for D. The D, now if you rearrange this formula, then cube root of 16 times T, 16 times 764 Newton meter divided by pi times the tau allowed 150 Newton mm squared. Now I have converted this Newton mm squared into meter squared because it is in meter, right? So I have multiplied 150 times 10 to the power 6. So I got the value of 0.029. Now the diameter is in meter. So I am going to convert this meter unit into mm by again multiplying 1000. So the shaft diameter is 29 mm. So we are going to select the standard shaft diameter 30 mm for this design. Okay. Now let's design the key as a mechanical fuse. Okay. Let's take this 18 mm as key width. Key we know already. Key will be looking like this. Okay. And the tau allowed is Newton mm squared, and the tau of the key means the allowable shear stress for the key. After that, the key will fail, it will break. So 150 Newton mm squared is the maximum allowed. Using that, the failure mode formula, um, uh, assuming that or taking that, considering first width, the key width as 18 mm. At the dia already we have found out D is equal to 30 mm. Okay, 30 mm. Sorry, we can take it wherever we want. So T is equal to 30 mm. I have rounded off. Okay, you rounded off this to 20 mm, and the T is now using the formula. T is tau allowed. I mean, tau allowed is nothing but the torsional stress at which the key will fail. So into the width times length of the key times d by 2. So you rearrange the equation for finding out solving for L. So T divided by tau allow into W times d by 2. That is equal to T is now in Newton meter, right? So I'm going to convert it into Newton mm. Okay, Newton mm, millimeters. Newton times millimeter. It is in Newton meter. The T is the torque allowable. I mean the maximum torque which is acting on the shaft at the speed and RPM to transfer the power of 120 kilowatt. So 764 into 764 Newton meter is now 764 times 1000 Newton mm divided by 150 is the Newton per mm square. This is also in mm, and 18 mm, and 15 mm is the diameter, 30 divided by 2. That is equal to 18.18. Let's take 18. So this keyway will be equal looking like a square keyway. Okay, square key. And bolt design. Pitch diameter, let's assume that as a 150 mm, and we have 4 bolts. Let's take 4 bolts. Okay, and the pitch diameter is the bolt circle diameter, PCD. So 150 mm, and the diameter divided by 2 is the radius of the pitch circle. Then this the formula for each bolt resists a particular torque at beyond which it will fail. So that torque, it's like the point at which it's going to fail. We are going to find out at that point what is the bolt we can select with the maximum factor of safety also. Okay, the bolt now here is we have the formula F is equal to T divided by N into RB. Okay, and that 764 is Newton meter divided by 4 times 4 bolts. We are going to design for 4 bolts with the bolt circle radius of 75, which is in mm. So I am dividing it with 1000 so that it will become meter. Okay, it's 2546 Newton. This meter and this meter cancelled, and the force comes in Newton only. Okay, Newton. The shear area is now nothing but the shear area is force divided by shear stress. Shear stress again nothing but force by area. Okay, the area will go to the top. So A is equal to the force 2546 divided by 150 into again the shear stress here is I'm going to make it to meter. Okay, meter squared, meter, Newton meter. Okay, that's why this value. So if you calculate for D bolt, that D bolt is square root of 4 times 8 will be 4 numbers of bolt meaning area of the at which the shear stress acts divided by 5. This is in mm. So you take 3 times the bolt dia, you will get 14. So let us approximate it to 16 dia. Or otherwise, if you want to put it in 4 times, also then you are going to select it. Select again 16 dia or somewhere near to that. It's like approximating, but not to fail before that. Okay. And flange and hub thickness are calculated using the standards, using ANSI standard BU 11.7, something like that is there. So if you take 1.25 times the diameter, you will get the flange thickness and hub length also. Okay. These are all the design calculations we have to do for a simple flange design. After designing this, I have inputted that parameters like this. Let us take this, and these are all the outputs I have generated from this design calculation, so that we can modify for different force, different power, and different speed requirements. What is the required diameter, and how the flange will look like. Okay. Now I have created a space basic 3D model with the design intents using the revolve command. And in this, if you see a difference in this model, if you see the relations, I have created all the relations that link to the Mathcad. But here I have not done that. I will do it one by one. For example, let us see the dimensions here. These are all the dimensions we are going to design. Okay, this one is a shaft dia, right? The D26. Okay, the D26, we can take it from, okay, this one, let's take it first, go back. Okay, this is what we are going to do. Now in the applications, you can open it's already there. The Mathcad worksheet is there, and so you open it. It's there. This is same. Oh my God! The real shape. Okay. This one we will close it, save it, and this one let us wait and see. Let us remove it. Okay, and then let us insert the worksheet. Okay. Okay. Now a bit up up to date. Let's see. Ah, this is what we have done right now, right? It's all saved. Okay, these are all the things I have typed myself, like shaft diameter. This one is taken 30 is taken as an output. So you can assign it as an output and show us. So for example, I'm going to create again shaft diameter. Shaft diameter. Okay. Um, I'm okay. I'm taking D and let me see whether it's creating value. Okay, it is 30 Okay, I'm going to assign outputs. So this one has come here. If I edit this variable name like shaft diameter, shaft diameter. Okay, the same shaft diameter is already there. It's deleted. Okay, now it's not a problem. I have removed this and assigned it. Okay, like that I have created for all these outputs in this tab. Now, now we are going to assign. Okay, once it's done, then Mathcad, you have to save and buffer. Save and push it. Okay, save and push it. Then we are going to the tools and see the relations, and in the relations instead of D1 is number. Okay, we can take it out and insert. Okay, insert from list and look in the inverter Mathcad for hub length. This is the parameter from that list, output list we have created. Insert it. Okay, and for D1 we have created. Okay, and for D6 is the flange thickness, right? Back and insert from the list and look in embedded Mathcad and take the flange thickness, insert the selected. The third one is now D26. This is the shaft diameter. Okay, the shaft diameter again. Let us insert from the list and look in embedded Mathcad and take the shaft diameter. Like 3 points apart. This one will look like, yes. These are all now have taken centimeters. Now we can go and see that this design parameter has been applied there. If you go there and see that parameters, yes, see that parameters and look inside the inverter, see these things. There's both sizes, 16 mm, it's 1.6 centimeter. Okay, it is flange outer diameter is 27 centimeter instead of 270 mm. I think this is 270 mm is itself is a bigger size. But anyway, it looks nice. We can control it. Thus we are going to iterate it. This one should be 2.5 times. 2.5 times. We monitor everything. Okay, save and push. Okay, go back there and regenerate the model. Yes. Okay, now again the PCB we have changed. Tools, relations, PCB is 6. We have reduced by 0.5. That means it's almost like a half of the circle diameter. Regenerate it. Yes. Tools, creations. Some 65 times PCD. Then again like this, where does it rate it? It should be 6 times nice. Or yes. Now the flag is completely with the width. 18 mm looks normal. So go back here, go back to Mathcad and see why we have assumed the key width as 18 mm. Instead of that, I will assume key width as 12 mm. And if this is 12, let's try same. And what should be the key? Same. 12. Now it's going high, man. this calculation because it's the smallest one. We have to take minimum basic things. Like you take 10 mm, and you go for this 10 mm again. Um, and choose 10 mm by 10 mm square. Otherwise, it will disturb steps. And save and push it. Okay, go back there. Regenerate it. Yes, it's square. Now it looks nice, right? Yes, it's what our flange nail parties. Thank you. Thank you for watching.